name is Frank Sanders. I'm the head of the Telecommunications Theory Division at the Institute for Telecommunication Sciences, a laboratory of the National Telecommunications and Information Administration, NTIA, located in Boulder, Colorado. Over the past 30 years, we've developed a series of techniques for measuring emissions from various types of radio emitters. In particular, we've developed techniques for measuring emissions from radar transmitters. In this series of talks, I will begin by describing the fundamentals of RF measurement techniques, and I will culminate the series by describing our techniques for measuring emissions from radar systems, techniques that hopefully you can implement yourself. Accompanying this series of talks are notes available on our website and also NTIA reports that you may find useful. We hope that you will enjoy watching this series of videos as much as we've enjoyed producing them. Welcome to the 8th talk in the ITS RF Seminar Series. My name is Frank Sanders, and in this talk I'm going to discuss a radar measurement system design. I say a because there's more than one way to build a system to measure radar emissions, but I'm going to demonstrate in this talk the design and the actual hardware construction of the system that we use here at ITS, and which in fact we've been in the process of developing for about 30 years now. We started these measurements with this type of design about in 1978. So that's what we'll be doing. Now, in the talks up to this point, we've examined the problems of how general radio spectrum measurement systems work. We've also, in the most recent talk, number 7, discussed the difficulties of measuring radar emissions. And I'm going to briefly recap what the problems are. There are really 3 major problems, or difficulties in radar emission measurements. And the difficulties are, number 1, radar signals have a low probability of intercept. When I say a low probability of intercept, going back to the talk even before number 7 where we discussed how radars are designed and how they're built, recall that a radar typically is transmitting pulses that are only on for 0.1% of the time. In other words, the ratio of the pulse width to the interval between pulses for many radar types is about 0.1%. On top of that, we have the problem that the radar beam itself, as it scans through space, is only momentarily present. Typically, a radar beam will itself be present for something like, for a long-range air search, air traffic control radar, 20 milliseconds out of every 12 seconds of time. In other words, the beam hits us at our measurement location for about 20 milliseconds. In that time, it puts about 20 pulses in our direction at this low duty cycle, and then for the remaining interval, which is almost 12 seconds, we don't see it at all. So, low probability of intercept for the radar signals, and coupled with that are the next 2 problems, which are that we're looking for a wide dynamic range in the measurement. Wide dynamic range is needed. Recall that for the NTIA radar spectrum engineering criterion, where we want to see how well the radar emission fits under a spectrum mask that looks like that, where the radar emission is down here, hopefully below this mask, that the dynamic range that we need to see from the peak level of the radar emission down here into this part of the radar spectrum is anywhere from 70 to 90 dB, so we need at least 90 dB, and on top of that, for other purposes, in which we're trying to resolve interference problems, we're actually looking for 100 to 130 dB of dynamic range. So we need 100 to 130 dB of dynamic range. And thirdly, we need good or high sensitivity in our measurement system, which means a noise figure that's on the order of, if possible, 5 to hopefully not more than 10 dB noise figure in the measurement. So these are the three problems. We want a very sensitive measurement system such that our measurement system noise floor is somewhere down here, good sensitivity. We need wide dynamic range so we can see a very, very strong signal, hopefully 100 to 130 dB above that measurement system noise floor. And we've got the problem that the radar signals themselves have a low probability of intercept. They're hard to catch. And in the talk before this, talk number 7, we discussed the difficulty of using a spectrum analyzer that's simply sweeping across the spectrum to meet these needs. First of all, the frequency sweeping behavior of a spectrum analyzer is not an efficient way to pick up the low probability of intercept radar signals. Second of all, a spectrum analyzer, any spectrum analyzer, is only going to have about 60 to maybe 70 dB of dynamic range available right on the screen as you're looking at it. And we need to get anywhere from 70 to 90 to 100 to 130 dB of dynamic range. So the spectrum analyzer, on its best day, might barely be able to get us enough dynamic range if we only need 70. Other than that, we're not going to get enough with a spectrum analyzer simply sweeping across the spectrum. And lastly, a spectrum analyzer typically will have a 20 to 25 to 30 to 35 to even 40 or 45 dB noise figure, depending upon what frequency it's being operated at and depending upon whether or not it has a low noise amplifier available inside its front end. And again, we've discussed this problem in spectrum analyzer design in earlier talks in the series. So given that these are our requirements, given that we have a hard time building a spectrum analyzer to simply sweep across the spectrum, how can we do this? Well, I'll draw a picture of the spectrum and we'll look first at the problem of dynamic range, even though I listed it as number 2. We'll come back to the other two problems because when we solve the dynamic range problem, we'll see that we can also solve the other two problems pretty quickly along with it. So, dynamic range. How do we solve that problem to get wide dynamic range in our measurement? Suppose that this is our spectrum that we're going to measure, and the radar emission looks something like this. We'll put a little magnetron hump in here and then come up to the main emission, and then we'll watch the emission roll off like that. And we'll suppose that everything is going to be measured from this level down. So in a relative sense, we'll call this 0 dB. And then coming down from 0, we'll say that we have 10, 20, 30, 40, 50, 60, 70, 80, can't count, 80, 90, 100, 110 dB down from this fundamental level. And we're trying to make a measurement across this range. Now the problem that we have with the spectrum analyzer, if we're simply trying to sweep across here, this is, by the way, frequency. The problem is that this ruler represents about the dynamic range of a spectrum analyzer in its sweeping mode. We're going from 0 to 60 dB down. So here's the dynamic range available in our measurement system, here's the dynamic range we're trying to measure across. What can we do about this? Well, we can do that if we could get enough sensitivity at the front end of the spectrum analyzer to see this signal right in here at that point, that we could then measure the emissions in this radar spectrum until we hit this level right here. And if we tried to do that, we'd be able to measure this part of the spectrum up to this point, and then beyond that point we would start to limit or saturate on our measurement, and then when we got to this point we'd start to be able to measure the spectrum again, obviously. So we think, well, what we'd like to do is then maybe start measuring this part of the spectrum over here where the levels are really low, and then when we get into this part of the spectrum, we would like to somehow adjust our dynamic range up. But initially the problem is that if we're measuring these emissions down in here at, say, this frequency right here, not only will we be saturating in this part of the spectrum when we try to do the swept spectrum measurement, but this power level here will actually be saturating the spectrum analyzer at this frequency, F sub center, like so, even though we're trying to measure out here at F sub mes. Now, here's one way that you can do this measurement, as I've diagrammed here. If you're trapped on a desert island and you've got no other options available, you don't know what to do, you can obtain, by hook or by crook, a notch filter. A notch filter which might have a passband that looks like this, such that basically the notch has 0 dB of attenuation across this frequency range here and across this frequency range here. In other words, it doesn't attenuate across these frequencies, could be tuned such that its tune frequency is at or close to the center frequency of the radar. It would have the effect of selectively attenuating the radar signal down in here, and then we could go ahead and perform our measurement across this part of the spectrum in here. We can even keep the measurement running through here even though the spectrum is notched out, and then we can remove the notch filter from the measurement system, like so. We go ahead and remove the notch, and then we take the spectrum analyzer at its input and we insert attenuation. And we put in how much attenuation would we need. Well, if this was the measurement system noise floor right here, and we want to measure this level up here, we need to put in enough attenuation to bring the spectrum analyzer's noise floor up to about this point right here. And that's going to be 10, 20, 30, 40, 50, 60 dB. So what we could do, having removed the notch and having already measured this part of the spectrum through here, like so, with the notch in, is then turn on or insert 60 dB of RF attenuation at the spectrum analyzer's front end, such that the spectrum analyzer's noise floor is now here, and we can't see these emissions anymore down here. But now we can measure across the center part of the spectrum, and we've got enough dynamic range available to do that. And I have done it that way. And it's a perfectly feasible method of making the measurement. It has a couple of disadvantages. One of the disadvantages is that you've got to get this notch filter tuned to exactly the right frequency, and it will only work if, and this is the real problem, if the radar is itself only putting out strong emissions on a single frequency or a couple frequencies that are close together. Unfortunately for us, but fortunately for me in the sense that I like to do this kind of work, a lot of radars, and nowadays most radars, I dare say, do not transmit on a single frequency, but rather, and this goes back to the talk that we had about radar system design, radars nowadays typically have emissions which will look like this. And then I'm going to erase this part. And here, they will have several available operational frequencies. And as we talked about in the discussion on radar system design, they do this both to mitigate effects of interference and also to mitigate poor propagation characteristics on particular frequencies. Another thing that some radars do, and we talked about this also, is sometimes they will simply operate like that. They do not have a set of discrete frequencies in here. What these radars do is to, in fact, operate with continuous emission all the way across some portion of the spectrum. These are the so-called chirp frequency radars. And in this radar design, just to refresh our memories, when the radar pulse, which looks like this in the time domain, turns on and then off, while the pulse is turned on, if we look at the pulse in the frequency domain, here's frequency, at the same times as we have here, it starts at some, actually here I'll do it this way, excuse me. Here's time again. Time, frequency versus time and power on this little display. What happens here is when the radar pulse turns on at this point in time, it starts at some low frequency and then the frequency increases right up to this point in time when the pulse turns off, and then it switches off like that. So it sweeps across this frequency range here on this diagram, which corresponds to this frequency range when we look at the spectrum. Now, if a radar is either frequency hopping or chirping, the notch filter option either won't work at all or won't work well. And the reason is because the notch is basically going to look like this. And we won't be able to typically notch out all of that energy at the radar fundamental. We'll be left with at least some of that energy not notched out. And again, when we're trying to make a measurement down here, that energy at that fundamental is going to saturate the front end of the measurement system. So, given that notches can be used on some radars, but that they have limited utility as a general purpose measurement solution, because what we want is a solution that will work for any radar, anywhere, anytime that we may be called, what can we do? Well, what we do is to abandon entirely the approach in which we operate a spectrum analyzer that sweeps across a given frequency range like this. Instead, we do it this way. We set up the measurement system, we set up the spectrum analyzer such that it is tuned to a single frequency on which we're going to do a measurement, fmes, and in the next talk after this one I'll discuss this algorithm in more detail. And when we tune it to this particular frequency, we actually set up the spectrum analyzer such that if this is the spectrum analyzer screen, we are in a 0 hertz span mode. We no longer look across a range of frequencies with the spectrum analyzer. We actually now look in time on the spectrum analyzer screen like this at a single frequency on which we're performing a measurement. So we tune the measurement system to this one single frequency, and we measure the radar emission at this frequency, and we put a band pass filter, which I'm going to draw in green, and I'm going to erase this material right here. We put a band pass, not a notch filter, at the front end of the spectrum measurement system, and our band pass filter looks like this in terms of rejection, where again this is 0 dB of rejection. The band pass filter looks like this right here. Okay? We make a measurement here on this frequency such that the measurement system now is only seeing energy across this frequency range right in here. Then, when we get the radar's peak emission level, which we do by waiting in time until the radar's done a complete beam scan, we'll talk more about this in a second, then we move the measurement frequency up a little bit higher, we'll talk about how much higher in a minute, to the second measurement frequency, so this becomes FMES1, this becomes FMES2, and we move this bandpass filter sideways just a bit. We move the bandpass filter itself sideways this way by just the amount that we moved the tuned measurement frequency down here. So now you see what's happening. We make a measurement on a single frequency, we get the data for the amount of power that the radar is emitting at that frequency, we step our measurement frequency a little higher at a later point in time, we'll talk about how much higher later, and then we move the bandpass filter along with it. And now we continue this sideways stepping action with the bandpass filter and with the tuned frequencies on which we're performing a measurement, increment by increment by increment by increment. And as we do this, what's going to happen here? Well, at first, as we walk our way across from this point right here to this point right here, where we measure that level, and so forth on across, as we walk our way across here, power's getting higher, power's getting higher, power is getting higher, we say, hey, wait a minute, we're starting to really run out of dynamic range at this point. At this point right here, for example, we're down to about 30 dB of dynamic range left before we're going to run out of dynamic range roundabout in here. So what we can do at this point is insert attenuation into the measurement system's front end. When we get to this point here, we'll add 10 dB of attenuation right there, add 10 dB of attenuation at this point right here. So now the measurement system noise floor is no longer here where we started. Now the measurement system noise floor at this point is here. And now our dynamic range at this point doesn't look like that. Now our dynamic range at this point looks like that. So we just moved the top of our dynamic range up to here. And then as we walk along to here, we might say, we'll add even a little more attenuation, step it up by another 10 dB at this point, and so now our measurement system's dynamic range is up at this point. And then as we continue to walk our way across the spectrum, we actually see the power drop. We might even take some attenuation out at this point. But now as we start into this part of the spectrum, stepping our way across, we make a measurement at this frequency, then we make a measurement at that frequency, now it's starting to go up really fast. So now we add 10 dB of attenuation here, and so now our dynamic range looks like that. Then we step to another measurement frequency here. We say, whoa, running out of dynamic range in a hurry. So now we add another 10 dB of dynamic range and step up like that. Then we come to the next measurement frequency where the radar power is hitting here, and we step our dynamic range up like that. And that's barely enough because the way I've drawn this radar, it's coming up really fast as we walk across some frequency. And so we immediately add another 10 dB of dynamic range at this point right here to bring our noise level up like that and put the saturation point of our measurement system up here. And now from this point forward, we walk our way across the spectrum to here with all this attenuation inserted, which the way I've drawn it is in fact 10, 20, 30, 40, 50, 60 dB of 60 dB of RF attenuation. And we actually have 70 dB of RF attenuation in our measurement systems. 60 dB of RF attenuation that we keep in from this point all the way across over to here, basically. And at this point, as the radar emissions begin to drop off as we step our way through the spectrum, we start to take the attenuation out as we walk our way along, and we come down like that until we, not like that, but come down like this until our measurement system gets back down to 0 dB of RF attenuation from this frequency forward, the way that I've drawn it on the board. In other words, by stepping our way through the spectrum and stopping on each frequency step and taking a measurement and then stepping to the next frequency, we're able to interactively do this with our dynamic range. Walk across, step up, walk across, step up, walk across, come up, step up, walk across like that, and then start bringing the attenuation in the system down and bring our dynamic range back down like that. Now, if you could dynamically switch attenuation in and out on a spectrum analyzer as it swept across, then you could do that by sweeping. But that is not a capability that's ever been designed into a spectrum analyzer. So the only way that we've ever found to solve the dynamic range problem is to, in fact, step our way across. And so, to solve this problem, the key to dynamic range problem is solved by stepping in frequency. Now, in the next talk that I do, we'll talk more about this particular measurement algorithm where we step our way across the spectrum. But I wanted to get the key to that principle described here, because this goes to how we're going to build the measurement system front ends, which I'm going to show in the lab section in this talk. So much for stepping. Now, stepping to solve the dynamic range problem. Now, we have two other problems. Having solved this problem by stepping, let's look at the second problem, the low probability of intercept problem. This too, as it turns out, is a problem that is solved by stepping. Stepping our way across the spectrum. Okay, we'll erase this. Okay, we already discussed the fact that the radar emission spectrum, which may look like this with a bunch of separate frequencies, and then comes down like this, means that the radar itself may well be hopping from frequency 1 to frequency 2 and so forth across up to frequency f sub n on a moment-to-moment basis, every few pulses, every 5 pulses, every 10 pulses, every 20 pulses. It depends on how the radar is built. It may be switching back and forth in frequency. While it's doing that, we know that the radar beam itself is scanning through space like this, if it's a simple air traffic control radar, and if it's a three-dimensional radar, the beam in fact may be doing this behavior, coming up in elevation angle, then turning off and dropping down, coming up in elevation angle, turning off and dropping down, and so forth, as it's rotating in azimuth. That makes it even more complex. So we're changing frequencies while we're changing azimuths, while we're changing elevation angles, all simultaneously. And in some types of three-dimensional radars, it doesn't even do this in any regular way. It may actually fire a beam in this direction for 10 or 20 pulses to look at a particular target. Then it may go into a search mode where it's going back and forth like this. Then it may break another beam out in this direction to track another target. So we can have a very complex beam scanning behavior, in space. As well as all sorts of complex frequency hopping or frequency diversity behavior. And so we, sitting at a point in space trying to make the measurement, just don't know exactly what's going to come out of this radar next, either in frequency or in direction in space. But If we undertake the stepping approach to making the measurement, it turns out we don't care. And here's why we don't care. One thing that I can guarantee that a radar will do, unless it's tracking a particular target in a particular environment like a test range, is it will have a sort of a search mode algorithm where every so often it's got to look in our direction. And the reason is because when someone's operating a radar, they don't want they don't want the radar to not see a target in any given direction. We're in some direction. Eventually that radar is going to come over and look in our direction to see if there's anything over there. Okay, so that means if we were to look at this radar emission on a given frequency, we'll call this just a frequency of measurement. If we look at that frequency in time versus detected power, and let's say that we let this thing run here for 60 seconds. For 60 seconds out to this point. Here's what we're going to see. We're going to see the radar. Oh, and this is our measurement system noise floor. Here's the measurement system noise floor. We're going to see the radar do something like this. We'll see the side lobe behavior as the beam is either being scanned or as it's rotating, and then boom, we'll see it hit us like this. It'll come up hard, hit us like that, drop out. I'm going to use a different color here that draws better. Use blue again. Okay, so you see the side lobe as the thing's rotating, comes up and hits us. Maybe it even does that. Let's say it's a really complex radar, complex frequency hopping, complex beam scanning, everything. So it does something like this. Boom, hits us again, and then waits for a while. Boom, hits us again. And let's say this happened across a span of 60 seconds. We say, that's interesting. And in fact, actually a little more realistic way to draw this, I'll put in one extra hit right here. Would be one extra hit right here, okay. So what's going on here? Well, the radar has some complex operation where it may be tracking targets, doing some kind of a search interleaved with that. It appears, when you look at this, that from any given moment when the radar does apparently look in our direction, because we know that this thing seems to hit this maximum level every so often, we can look at this and we can say, okay, well, the radar waited that long before it looked over in our direction again, and then it looked in our direction again in a little shorter interval, and then it looked in our direction again in an even shorter interval after that. And if we were to watch this even longer, let's say we did watch it even longer, we might see a longer interval, and then we might see it come up in a shorter interval, like so. So we start looking at this, and I've done this, we start looking at this and we say, let's suppose that this turned out to be an interval of 20 seconds. 20 seconds. And then we say, this was an interval of about 15 seconds. And this was an interval of maybe 10 seconds. Oh, and then it was an interval of 20 seconds again. And then we had an interval of maybe 10 seconds. We say, oh, look what they're doing. They never wait more than 20 seconds before they come back to search. That tells us what was going on in the mind of the designer. They didn't ever want to leave a sector unexamined for more than 20 seconds. So whatever that radar is doing, it comes back at least in 20 seconds. It may come back sooner, but it never waits longer than 20 seconds. And if you keep playing this for several more minutes, you'll see that, in fact, that's going to be the case. Now, for a lot of radars, it's not 20 seconds. For a lot of radars, it turns out to be 10 or 12 seconds. Which, interestingly enough, is the interval for a long-range air search radar if it's simply rotating mechanically. It's the same problem. They don't want to not look in a certain direction for more than a certain amount of time before they look again. So they say, oh, so suppose we want to measure this radar with the stepping algorithm we just talked about. If, for every measured frequency that we examine, we run the spectrum analyzer for an interval of time that's a little longer than 20 seconds, we'll say maybe 22 seconds for good measure, then we know that we'll always see the radar look in our direction within that interval. And if you don't believe me, watch the radar for 5 or 10 minutes and see if it ever goes for less than 20 seconds, or whatever that interval turns out to be for that radar. I mean, it might be 10 or 12 seconds, but whatever that interval is, you'll watch this. And even for the most complex beam scanning radars, this will happen because they can't not look in a certain direction for too long an interval of time because somebody in effect may be sneaking up on you. So now we know that if we were to set up our spectrum analyzer in that stepping algorithm mode that I just discussed, which solves the dynamic range problem because we can keep adjusting our dynamic range as we step across, we also know that if we set up our spectrum analyzer for this particular radar such that it sweeps in time on a single frequency on which we're making a measurement for this magic interval, which we determine by watching the radar emission for a few minutes, then we know that at some point, we don't know which point, at some point in there, it's going to do that, like that. Then we know that if we simply always take off of the spectrum analyzer as a data point the maximum power level that occurred within that magic interval of time, in this case 20 seconds, but it could be 10 or 12 or 5, whatever that interval is, then we know that we just measured the maximum amount of power that the radar will put out on that frequency. And we can record that in a measurement spectrum over here, which I'll draw like this. This is the spectrum measurement. We know that at that frequency, fmes, which we'll draw right here, there's fmes, we know that the radar hit that power level right there, and that was the highest power level that it's going to put out in that direction because we waited long enough to make sure that we'd see a maximum amplitude hit occur. Then we step to the next frequency. We adjust the amount of attenuation in the front end of our measurement system, if necessary, to keep the radar emission within that magic dynamic range of the measurement system, and we wait for another 20 seconds. And when we do that on the second sweep across on the spectrum analyzer, since the first sweep now will be erased, we watch the spectrum analyzer run, and this time, by sheer random accident, that maximum level occurs almost immediately, and then we see some side lobe behavior like this. We might even see another kind of high hit there for some reason, but not quite as high as the first one. And again, we run that out to 20 seconds, and again, we pull off the maximum power level that occurred in that 20-second interval. We plot that power level on the spectrum at the second frequency right there, like so. And so now we gradually build our spectrum up like this, step by step by step by step. I'll draw it as kind of a simple spectrum till we max out, and then we come down step by step by step. And just to make it easy on ourselves, we connect the dots, and there's our emission spectrum connected step by step by step, like this, like so. And so now we've solved both the probability of intercept problem. We don't care how complex the radar's behavior is. We just wait on a single frequency for a long enough amount of time to get its maximum emission in our direction in that interval, and we adjust our dynamic range as we walk our way through the spectrum like that, and so forth, right through there, and then come back down like that, using an RF attenuator at the front end. And so now that solves that stepping behavior, that stepping algorithm, as long as you use the right, and by right I mean long enough. And by the way, you can't go too long. The only thing that'll happen if you go too long is you'll just waste time on the measurement. For example, if we were to go for 20, not for 20 seconds, but for 30 or 40 or 50 seconds, we typically get 2 hits from the radar, but it wouldn't hurt us to go too long. You just don't want to go too short. But if we wait long enough for this magic interval, we will always solve the probability of intercept problem for a given radar type. So again, this problem, that radar signals have a low probability of intercept, is also solved by stepping our way through. Now, the third problem, getting a good sensitivity, well, we know in effect how to solve that problem, and that's by putting a low noise amplifier at the front end of the spectrum measurement system. I just happen to have one right here today. We'll do a close-up of this during the lab, but a low noise amplifier at the front end with the appropriate amount of gain
should give us the best possible sensitivity for the measurement. And in an earlier talk, we discussed the derivation of the Reese equation, and we saw how to get the right noise figure and gain combination in an amplifier at the measurement system front end. Okay, now, let's build the measurement system on the board then. Here's how we're going to do it. First of all, we'll draw out a spectrum analyzer. And now, the spectrum analyzer at the front end has a variable RF attenuator. We'll say it's 0 to 70 dB. A variable RF attenuation. And then the spectrum analyzer has an option, typically, as you'll recall, where we can either turn on a preamp or not turn on a preamp. Let's just assume that we go ahead and turn on the preamp here at the front end. But I'll show you what the problem is with that in a moment. So we turn on the preamp, the low noise amplifier, here at the front end, and we then go into a mixer, and we probably have multiple mixing stages, and this gets us into the IF. And we've talked about all that before. Now, I've actually left something out of the diagram here intentionally. If we were to build this kind of measurement system at the front end, or use this kind of configuration, if we were to use this kind of configuration at the front end of a spectrum analyzer, we know that the problem is that if, in the frequency domain, here's frequency, if the radar emission spectrum looks like this, and if the low noise amplifier's response, gain response, looks like, say, that the problem is that this radar emission is going to overload the LNA at this frequency. And even if the frequency of interest to us that we're looking at is way up here, here's FMES, it's way up here, even though we're measuring here, this low noise amplifier, the way I've drawn it in this diagram, is going to be overloaded by that energy down here at frequency F sub 0. Okay, what do we need to do? Well, we just talked about it a minute ago. We need to put some kind of filtering in here, and it is true that in most, if not all, spectrum analyzer designs where there's a low noise amplifier in the design, that between the RF attenuator here at the input, between the RF attenuator and the LNA, we have some kind of a filter. Now, unfortunately, in a lot of designs, at lower frequencies, this filter is a low-pass filter, which in a lot of designs, for example, is a low-pass that passes energy all the way from 0 to 3,000 megahertz. So the problem here is that if this radar were, for the sake of argument, let's say operating at 1250 megahertz, that filter at the front end would have a passband characteristic that looks like that. It's actually passing energy all the way across there, and so having that low noise amplifier in there after that low pass means that that LNA is still going to be overloaded by all this energy all the way across, including this fundamental energy right here. Now, it is true also that in a lot of spectrum analyzer designs, that at frequencies above about 3,000 megahertz, this filter is switched out for a tunable bandpass filter, which I drew a few minutes ago, which is based on yttrium iron garnet technology, and that is a good filter design to have. But unfortunately, that only occurs in most, if not all, spectrum analyzer designs for frequencies that are greater than 3 gigahertz, like so. Okay, so if you just buy a spectrum analyzer off the shelf and you try to implement the stepping routine that I just discussed, you may be able to use the stepping routine for frequencies above 3 gigahertz because there's a yttrium iron garnet filter, which we'll talk about more in a minute, at the front end, which is a band pass filter. Oh, I need to correct this at this point, which is a band pass filter. But as I said, when you switch the analyzer to frequencies less than 3 gigahertz, that gets switched to a low-pass filter, and the low-pass filter is typically wide open from 0 to 3, and it means that if you are measuring this kind of radar emission at a frequency that's below 3 gigahertz, that low-noise amplifier at the front end will be overloaded. All right, and again, what do we want? We want a general-purpose solution that works for any radar at any possible frequency. So, oh, and there's one other little problem here. Sometimes the performance of this LNA is not as high as we'd like, and some spectrum analyzers don't have any LNA in here at all. Some spectrum analyzers have the attenuator, the filter section, and then they go straight into the mixer. This is especially the case for older spectrum analyzers. It's also the case that for analyzers that do have a preamplifier available, here's another one that gets you. At frequencies above 3 gigahertz, they often actually have this configuration as I've just drawn it, which is now you get the YIG above 3 gigahertz, and there's no preamp option available. Okay, we want both. We need at all frequencies. Here are the requirements. At all frequencies where we may be measuring a radar, we need both a tunable bandpass filter, try to draw here, right? A tunable bandpass filter, because the arrow here means it's tunable. This thing will track whatever frequency we're trying to measure down here at the IF. A tunable bandpass filter and an LNA, a low noise amplifier. Both. We need to get both. And we typically don't get both of these features, a tunable bandpass filter and an LNA, in the spectrum analyzer at all frequencies, You may get this combination on some frequencies. In some analyzers, you won't get it on all. So, here's what we've had to do. We've had to back ourselves out of the spectrum analyzer and put our own LNA up at the front, like so. So now, because we have our LNA at the front of the analyzer, we know that for all frequencies we have an LNA. And having done that, we now have to put the tunable bandpass filter here, like that. And I'm going to draw it with an arrow to indicate that it's tunable. A tunable bandpass filter here. Oh, and because it's tunable, what are we going to have to do? We're going to have to connect it via some kind of logic line back into the spectrum analyzer so that it knows what frequency we're tuned to. Unless you want to sit here with a manual filter and go for about 6 hours, or however long the measurement takes, which you don't want to do. So we run a logic line out of the spectrum analyzer, and luckily, many, if not all, spectrum analyzers have a YIG, yttrium iron garnet, tune, voltage, output on the back, where there's a voltage that comes out of the back of the spectrum analyzer, which is proportional to the tuned frequency of the spectrum analyzer, which can be used to control the tunable bandpass filter. And then, for the dynamic range problem, remember we also have the dynamic range issue. We need an attenuator, and this one's not going to do us any good because it's inside the analyzer. We've got to back an attenuator out here to the front end, like so. Okay, 0 to 70 dB of RF attenuation. Now, here's the funny part, here's the funny if not ironic part. What we've done here, as I've diagrammed it, is to draw a front end which we have to provide, which actually has components which in one sense or another are often redundant to what's inside the analyzer. That includes the low noise amplifier, and this is where we get our sensitivity, the necessary sensitivity. That was problem number 3 that we had in the introduction. And then we have the tunable bandpass filter to protect this thing from being overloaded when we're not tuned to the center frequency of the radar. So this protects from front-end overload, or solves front-end overload problem. And then we have the 0 to 70 dB RF attenuator, which solves the dynamic range problem. But we've had to build them all into our own box because you don't simultaneously get all 3 of these components operating together the way we need them to in any spectrum analyzer design that we've seen so far at all possible frequencies across which we may be making a measurement, which for radars is going to run anywhere, putting aside the HF radars, anywhere from about 400 megahertz on up. Certainly all the way from 400 megahertz up to 18 gigahertz. Oh, and by the way, regarding tunable bandpass filter technology, YIG technology typically works at frequencies equal to or greater than 500 megahertz. Below 500 megahertz, there are other electronically controlled tunable bandpass filters. They're called varactors. Okay, so here's what we need to do. And so ever since the late 1970s, we've been building these kinds of front ends into our measurement system. And just for good measure, we typically put these front ends up as close as we can to the measurement system antenna so that this line, this RF line that's running from the output of the front end into the spectrum analyzer, has its loss overdriven as much as possible, hopefully entirely, by the low noise amplifier. So we typically put these front ends right up at our antenna. To put another way, if we don't put this front end up at our measurement antenna, then whatever line loss we have between the antenna and the input here, the input to this front end, so say we have this line going up like this, up to a measurement antenna up here. If we don't put this thing close to the antenna, then all of the loss in this line, which could be 30, 40, 50, 60 feet, just depends on our situation, all of that loss in that line is simply equal to an increased system noise figure. Increased noise figure. And we want to keep that noise figure as low as possible. That's why we put an LNA here. So if we move this box up as close as possible to the antenna, that's good. Okay. That in essence is on paper what we need to do to measure a radar. We're going to operate the spectrum analyzer in a stepped frequency mode, which will in turn require that the analyzer be controlled from a computer, because you wouldn't want to have to step across all those frequencies manually, and in turn, or in complement to the step frequency mode on the spectrum analyzer where it's controlled by a computer, we build our own front end with its own LNA for good sensitivity, its own tunable bandpass filter, which is based on YIG, yttrium iron garnet technology, to protect this thing from overload at the radar center frequency as we walk our way, as we step our way across the spectrum, itself being controlled from inside the spectrum analyzer so that it knows where to tune, and then finally an RF attenuator at the front end that can range from 0 to 70 dB so that we can, again, walk our way up with attenuation values as we go through the fundamental frequency of the radar, and then come back down with this attenuator here at the front end as we come away from that high power region in the radar spectrum. That concludes the talk on the board, and we'll pick up with a lab session in just a few seconds here, in which Okay, this is the lab portion of talk number 8 on a radar measurement system. In this lab, we're just going to look at the hardware components that we discussed in the first part of the talk, and I'm going to show the components individually first, and then we'll show how we build them in the front-end boxes. First of all, at the front end of the measurement system, we typically put in an attenuator which can go anywhere from 0 to 70 dB, And this is one of the attenuator types that we use, and this attenuator is electronically controlled so that we don't have to operate this thing manually. We can operate it in a certain sense manually, but only via software. But we do have algorithms that will switch this attenuation automatically during the radar measurement. So here's a 0 to 70 dB RF attenuator. Now, following the attenuator, we have our tunable microwave bandpass filter, a yttrium iron garnet filter. This is what a YIG looks like in its packaged state from the manufacturer. The YIG itself is actually right in here. And it has an RF input port, an RF output port, and a couple of ports for the control voltage that come in. I'll show this in a minute in the form in which we put into the spectrum analyzer front ends. Then, following that, we have a low noise amplifier. This is a typical low noise amplifier. This particular amplifier operates from 100 megahertz to 1,000 megahertz. And we've talked in earlier discussions about how to get the right noise figure and gain for an amplifier like this. Here's something else we like to put into the front ends. We like to put a calibration source in. We haven't talked about noise diodes. We'll talk about those in a later talk. But this is a noise diode. This is a calibration source. And we like to put this into our front end also so that we can switch to it automatically, turn it on, look at the noise, verify that we have a path through our measurement system that works, and also get the actual gain and noise figure of our system at the frequencies at which we're going to measure, all with the noise diode. Here's something else that's necessary in our measurement systems typically. This is a box which contains a pair of op amps, and this box converts the voltage that comes out of the spectrum analyzer, which is proportional to the spectrum analyzer's tune voltage, to the proper voltage to operate with the YIG. If the YIG happens to have the same voltage requirements as the spectrum analyzer, we're lucky. If we're not lucky, then we use a box like this in the path to convert the analyzer voltage into the right voltages for the YIG. By the way, typical YIG control voltages are something like 1 gigahertz per volt. And then I have one other example here to show for a YIG. This is a YIG that's built into a package, which again comes from a manufacturer. But when we build our spectrum measurement systems, what we need to do is package all these items together. And to do that, we've always had to fabricate our own boxes. This is one of those boxes. It has a circuit board inside, and I'm going to let it sit here like this for just a moment. Unfortunately, I forgot to undo these 2 screws, which I will now drop and lose. But it's a nice design because the control circuit board flips open on this box like the hood of a car. There we go. Watch me drop it. Flips open like the hood of a car to reveal. Oh, I'm not going to go into the rest of it. I'll just hold it like this. To reveal what we would see. Can we see this okay? See here from the end, we have a set of components inside that include a noise diode right here. And here is a relay at the front end that will switch between the noise diode and any one of a number of antenna input ports so that we can have multiple antennas on our measurement system and switch between them electronically. And then, just under the circuit board now of the field of view is a YIG, a low noise amplifier, actually a set of low noise amplifiers, also a set of fixed band pass filters in addition to the YIG, and finally, after all of that processing, the output port, which is located right here. And this is the output port that then connects this into the rest of the measurement system. So all we do here is take a set of these discrete components, noise diode, RF attenuator, which is also out of view under the circuit board, and YIG filter, some fixed bandpass filters, and actually a set of low noise amplifiers so that we can optimize for a given frequency range measurement configuration, all inside the box with the relay positions inside the box controlled via the circuit card so that we can command the relays to get the right measurement path through the box, and with the voltage input for the YIG along with the other control voltages coming in on this logic port right here. Now, this particular box is one of my favorites, and if we ever have a disaster here at ITS, I'm taking this out first and coming back for survivors of the disaster later, because this is hard to replace. And they think I'm joking. Now, we have other front-end boxes which have better performance, although they're also a bit larger. They have the same functionality in every case. This is one, for example, which we use with our current measurement system. There we go. This box has better isolation. I'll turn it around like this. This box has better isolation than the small box. It's got these nice RF fingers running around it. It has better isolation on the power and the logic lines coming in, but in essence, it contains the same hardware inside. Here we have an RF input port, a couple of RF input ports. These come into front-end relays, which switch us into an attenuator here, first of all. And we also have a noise diode at the front end, which is used as a calibration source. The noise diode is right here behind the attenuator. Then, coming out of the attenuator, we go into the YIG filter section. Here's the YIG right down here. And then coming out of the YIG, we go into any one of a number of low noise amplifiers running along like this. We can pick the right amplifier using a relay. We have a lot of relays in here, of course, to switch the paths. These are the relays. And then finally, we have the output port coming out of the front end of the box right over here, and this again going into the rest of the measurement system. So this has the same functionality as the small box I just showed you, but it gets better isolation from strong signals with the YIG because it's a higher performance YIG. It's got a better noise figure than we have with the small box because the amplifiers in here have a little higher performance, and the box overall has better power supply and better RF shielding. So the price we pay is it's also a little bigger and heavier. So I'll come back if there's an emergency and get this box on the second run in. Then I'll get the survivors on the third trip. So if you're worried about me, you better get yourself out on your own, I guess. Now, these boxes also typically require some logic down inside the measurement system, inside our measurement system van, for example. This is a box that we use with a small front end. This is a controller for the YIG. It's bigger than it needs to be, but since it goes into our measurement system down inside the racks, we really don't care how big it is, so we just go ahead and build it into this bigger box. We also control these boxes via a serial connection or an Ethernet connection, and so in here we have a serial Ethernet adapter capability inside this control box, and I'm going to rotate it like this so that we can see inside it a little better, like so. All right. We also have power supplies in here that are used, which include typically 12 volts, 15 volts, and 28 volts. Here's one of the power supplies right here. I'll see if I can electrocute myself on it with the capacitance that's stored up. And as I say, this is a controller box for the front end, which we don't need to put up near the antenna that we're using for the measurements, so we just put this inside the rack, inside the measurement system. We have somewhat different configurations on this for the small front end versus the big front end, but the principle always remains the same. And in a certain sense, these front end boxes are sort of our secret weapon, because people say, well, how do you do these radar measurements? Well, the answer, aside from the stepped algorithm that I've described, is to build these kinds of front ends. And we have not found that these are really commercially available, so we simply build them ourselves, and then we operate them and maintain them ourselves as well. And that's as far as I want to go with this talk today. In the next talk, we'll actually run a spectrum measurement with some actual radar signals with these front ends. But this is the introduction so that you can see what we're doing and how we're doing it. Any questions? Okay, thanks for coming. That concludes talk number 8.